Welcome to our webinar on MicroSurvey STARNET. My name is Dave Filipski. I am the outside sales rep for Maine Technical Source. I cover all of upstate New York and Vermont for MTS. I've been with the company for about 15 years. So for those of you that don't know me, that's a little background on me. Before I introduce James, if you guys have questions, please put them into the chat. And at the end of James's presentation, we'll go through and answer all the questions that we can. We will be posting this, a recording of this webinar on our Maine Technical Source YouTube page, and we'll send you the link to that as well after the webinar is completed. So James, if you want to introduce yourself and get it kicked off, I'll pass it over to you.
Great. Okay. And yes, thanks, David, for inviting me to present, and thanks to Maine Technical Source for hosting this event. Yes, my name's James Johnston. I'm the technical support and training manager at MicroSurvey. I've been doing it for 19 years. For at least half the time, STARNET has been one of our products, and I do like to describe myself as the company's main STARNET enthusiast. I do love telling people how it works, and its approach to getting things done just completely appeals to people with a brain like mine, and yeah, to a lot of other enthusiasts that I get to talk to. So the purpose of this webinar is to highlight sort of a very truncated presentation of a workflow, and we're going to particularly focus on a data set in which tilt correction has been used, because there are special considerations and features in STARNET that help to accommodate that type of a sensor. And while I'm at it, I'll for those who haven't seen STARNET before, I'll give them kind of a quick overview on how to start a project and how to get things done. So on to the topic. So I thought I'd introduce this just by talking about what my general escalator pitch is as to why someone would want to add STARNET to their workflow. And it's triggered by me asking other people, hey, why do you think you need STARNET, or why do you like using STARNET? And there's always a big contrast. People who are new to STARNET but have heard of it, they'll always say, why would I want STARNET? Oh, well, it's because it gives me high precision. And people who actually use it, high precision is way further down on the list. They'll talk about how STARNET makes it really easy to find mistakes. They'll talk about how STARNET makes it really, really nice how they can present well-documented results with weighted results and things like that. They'll talk about a bunch of other features, how grid-to-ground combination is easy, and then way down the bottom, almost as a bonus, I get high precision. So I'll try and focus on that, and by the summary time, you'll be able to see where the advantages are of using STARNET, or in general least squares, but of course STARNET's the one that I like to tell people about. And so let's get into the first few of our slides, and then I'll start showing you how STARNET works. So first thing that I wanted to talk about is project configuration, and I'll focus on some of the settings that are going to be relevant in a project that is that is essentially a grid project. So we're going to be working in state plane coordinates, and STARNET is going to by default output grid coordinates, but there's also a tool that allows you to output ground coordinates. So the settings that I'll just give you a little demonstration on: units, we're going to select an appropriate state plane system. We're going to make sure that we've got a correct geoid, and I'm going to make sure that you see we've got the feature side shot detection on. So let me get into that. So we're going to bring up STARNET. And so I've got a job created, and I'll just review some of the key settings. So this is a project where our distance units are US feet. We'd like to do a 3D adjustment. I've checked on grid, and I've already assigned the Virginia Net83 state plane system. And to select a coordinate system for US users, you're almost always going to go into the coordinate system group. STARNET has 3,600 coordinate systems to choose from, but currently Americans are always going to be going into this. And then if I just hit the V key, I'll jump down to the Virginia North state plane zone. Geoid modeling we want to have a look at, and that's something that you assign over here. I've already got it assigned so that we're using a bin file that's been downloaded from the NGS website. If you're new to STARNET and you need to set up geoid modeling, if you pick on this info button here, then if you click on this link, that'll open up the MicroSurvey web page where you've got all the information about geoids, and you've got a whole bunch that you can download. And also down here, you've got the mapping folder. If you click on that, that just opens up the folder where you drop the geoids. And the final setting that I want to point out here is on the Special tab. There's a feature right here called Detect Side Shots, and with STARNET it's on by default, but I want to make sure you know that it's on, and that's going to make more sense later on in the presentation. Next, STARNET instrument settings. So an important aspect of using least squares adjustment at any level in any least squares program is that the system is dependent on the user accurately estimating what your error levels are going to be. So, you know, for example, if you did a survey with a 5-second instrument, you expect your closures and your results to be what you would normally expect from a 5-second instrument. It's important that you do that, because if you don't set realistic expectations, then your results don't necessarily make sense. Nice thing about almost all instruments that are sold nowadays is they'll be published with a spec sheet, and they'll have settings that are determined by the the ISO 17123 specification, or there's a DIN specification that essentially means the same thing. And if we look at the spec sheet of a Leica TS20, which we're going to be talking about during this presentation, you can select a 1 second, 2 second, 3 second, or 5 second edition, and so that's the number that is, you know, is calculated according to the ISO spec that we were talking about, and we can see that distance measurements are with a 1 millimeter constant and with a 1 ppm. So that's the information from the spec sheet that we want to look at so that we can start correctly, accurately estimating our errors. Now I'm going to go into the project settings, and actually let me just jump back to the PowerPoint and get to here. So these are the 5 things that I'm just going to talk about when we're looking at estimating standard errors. I already mentioned the ISO spec. I will open up instrument settings. I'm going to show you a little trick for accommodating the fact that most spec sheets give you metric specs when you're working in US feet. And I'll show you an online tool, the instrument settings calculator. Okay, so instrument settings, that's over here. So here's where, for a conventional data project, you want to specify what your instrument settings are. Now, and an easy way of populating it, I'm going to show you, is an online tool that I'm going to show you. And an easy way to get to that online tool is when you've got this open, hit the help button. STARNET help comes up. If you go all the way down to the bottom, after it explains all the formulas and so forth, there's a link to an online tool here This is the instrument settings calculator, and this allows you to input your ISO specs, answer a couple of questions about procedure, and it'll tell you how to populate your instrument settings. So let me go through this. So first question is, it's going to ask you, as you're turning your angles with your total station, how many angles do you average before you input it into STARNET? And I'm going to show you a procedure and some conversion options that will just count on you selecting 1 as your option here. That would be in the STARNET DVX converter if you just choose the all observations option. So if you are using any one of the many Captivate routines that allow you to take lots of robotic shots, and then at the end it'll either, it offers to average everything, and you may or may not decide to average them, but when you read the DVX file using the converter, we're just going to tell it, I want to see all the observations, and if there are any outliers in there, I'm going to use STARNET to weed them out. I don't need to do it in the field. So if we set it to 1, it's a straightforward way of doing things. And then after that, it's just a matter of answering a few more questions. So here's where I'm going to assume that, or actually I know that we're working with a 1-second instrument in the data set I'm going to show you. Further down, the EDM constant was listed as 0.001 meters, 1 millimeter, and the parts per million was listed as 1. I'll fly through the other questions here. It asks, how do you want to handle azimuth or bearing input? In most cases, this doesn't matter, and in this data set, it doesn't matter at all. And really, it only really matters if, for example, you're bringing a gyroscope or an astronomical observation in. Instrument centering error. So this is where you're deciding how well you are centering your instrument over the point on the ground. And so I'm going to estimate 1 millimeter here. Target centering error, and I'm going to talk metric, and you'll see why I'm doing it in a few minutes. Target centering error. Also, how well are you positioning the target? That would be, the prism on its tripod over the point on the ground, over the mark on the ground, or how well are you balancing the pole? So again, I'll estimate 1 millimeter. ATR centering error can be used to inflate this, but I'm just going to keep that at 0. So that's just how well do you think the instrument centers itself on the target. And vertical centering error, that's essentially how accurately are you measuring the instrument height and the target height with your pocket tape or with your auto height tool. And I'm also going to estimate 1 millimeter for that. And all of those estimations down here, these are ones where you don't have an ISO spec most of the time. That you either estimate for yourself and try and keep it reasonable, or there might be other more elaborate ways of computing them. But that's why, that just explains the reasoning behind what I'm doing. As soon as I pick on submit, then on this page, this section here, that tells you how to populate your instrument settings. And that is what I've done in here. So I've just copied those over. Now, the important thing that I mentioned was this is US feet, but remember I went through the instrument calculator and metric. All you have to do to translate that is just temporarily switch your project to meters, go over to the instrument settings, and then you just type them in exactly as they were shown on the calculator page. And then as soon as that's done, you just switch your project back to US feet. And they'll be applied as feet instead. See how that 1 millimeter is now shown as 3 thousandths of a foot. Okay, that's what I wanted to say about instrument settings. Okay, so now we're on to importing data. I'll give you a quick overview of importing, and then I'll give you a little bit more of a detailed walkthrough using the DVX converter. Okay, so all of the input is if you need to use a STARNET importer, then you'll find all your options under the input menu. If you have GPS data, so in most cases this would be post-processed GPS data, you just pick this up, you select the format that you're going to import, select the files, and they'll be added to the project in this input panel over here. I'm not going to be dealing with post-processed GPS. I am going to be dealing with RTK GPS. And for that, I'm going to use the Leica DBX converter. You'll see here in the menu, we've got a selection of other converters. I'll give you a few key examples. If you have Trimble equipment, then use the Job XML converter. If you have Field Genius, either Windows or Android, we've got a Field Genius converter. If you have Carlson, we've got a Carlson converter. If you have leveling data, for Leica, we've got the DNA converter. For Trimble, we've got the DNI converter. Let's open up the DBX converter. That's the only one I'll be showing you today. So when this comes up, I'll talk about a few of the options down here that are going to be significant. One of them, remember when we were back on the calculator page, I had mentioned that I want to weight our adjustment, assuming that we've got all shots and sets. So that's the option that I want there. So that means all of your redundant observations are going to be viewed in STARNET, and like I said, outliers will be handled using STARNET. Under the checkbox here for survey data, we're going to write M records. We're just going to keep things consistent. Want to make sure that we've got our distance units set to US feet, angular units set to degrees, minutes, and seconds. And I've got most of these options on. Coordinates or northeast order, that's on by default. Up here, you'll note that I've set a path to where I've got a huge collection of gem files, that is geoid files, for all over everywhere that I talk to customers. And the reason that that's there is whenever you're using the DBX converter, if you have used a geoid in Captivate when you're doing the work, then the converter needs to know which gem file you're using, and that's mainly so that it can calculate accurate scale factors. So I've already got this set up so that the gem file that was used in Captivate is already in this folder. Last thing to mention, I've checked on this option here, change dash characters to station names, or change dash characters in station names to underline. Reason that I've got that on is because with Captivate, when you're doing RTK GPS, Leica always makes up a name for your reference station, and it always puts a hyphen in it. And that hyphen kind of breaks STARNET's method of separating stations. And so the easiest way of adjusting that is just tell it, change the hyphen to, in this case, an underline. Okay, now I'll start doing some importing. So I'm going to hit Browse here, and I'm going to browse to the first of 2 data sets. We're going to open that, and I hit Import. Give it a minute. Oh no, because I am disconnected from the network, I don't have access to that gem file. Hang on while I get connected to the network. Okay, let's see if I can do that again. Okay, I fixed it. I was trying to turn off as many programs as I could before the webinar, and then that broke something. Okay, now that I've created my file, watch what happens over here in the data file list when I close the converter. So that data file has been created, it's been added to the input panel, and it's ready for me to work with. Now I'm going to use the DBX converter on a second data set. And I'm going to import that one. There we go. So the first data set we're going to find it's a bunch of control work. And the second data set, it's a little bit of control, but it's also some topo detail shots. And it's in the second data set where the AP20 was taken advantage of. So let's get back to the right title slide here. So we talked about using the DBX converter, and yes, I mentioned the support files, so that would be the geoid and so forth. Okay, now we're going to get into using STARNET. And first thing that I'm going to talk about is how it's really good as a project grows for you to look at it in small sets first and assess things as they go and make sure that your data is nice and clean. And then, so you notice how I've got a screenshot of the data input panel here, and I'm going to show you how you can use these check marks to turn data sets on and off. And I'm also going to talk about a inline option called data off. And then we'll talk about processing summary in a minute. I'll just get that slide ready. I'll come back to it. Okay, so let's first process. I just want to have a look at the WSSI data set, which has some control work in it. And let's even break it down further. So what I've got here is at the top, I've got a whole bunch of RTK data or RTK GPS shots. And then further down, we've got, these are called direction sets. I've got some conventional observations using, in this case, it's actually an MS60 total station, but the equivalent of a CS20 in terms of accuracy. And what I'd like to do to start with is process just the GPS. I'll leave the total station till later. So I'm going to go type in .data off. So that's just a way of telling STARNET, ignore everything that's below this line. And then a little further up, what we'll find here is the reference station that was used while Captivate was taking observations is this one here. It's already recorded what the state plane coordinate is, but there's a pound sign right here that comments it. It just turns that coordinate record into a comment. So to activate it, all I have to do is delete that hash mark, and this coordinate will now be part of the input, and this is significant here. Over here we've got 3 exclamation marks, and those just mean that because you've got 3 exclamation marks and you've got 1, 2, 3 coordinate values, those 3 items are going to be held as fixed during the adjustment. Okay, let's run the adjustment for the first time. We just hit the Adjust Network button here. Yes to the changes I've made. And in the plot now, we can see where we've got 4 stations, 1, 2, 3, 4, and we've got that fixed station shown by a red triangle in the middle. Let me also draw your attention to this important feature called the processing summary. And so this is where we usually call it the chi-square test takes place. And what I'll do is I'll bring up this slide here from the PowerPoint just to make clear what we're seeing. And so the processing summary, that's the first place you should look after you run the adjustment, because what you're wanting to see on the processing summary is you're going to have a look at this number here. That is the total error factor, and it's 0.970 in this case. And that is a number that expresses how well your estimated errors and how well your actual errors correlate. And so if you have a number of 1, that's a perfect adjustment. That means absolutely everything matched what your estimations were. I've been doing this for 10 years and I've never seen a 1, but as long as they get close to 1, that means you're in the right area. Now, there are various other scenarios. And so what's happening is this number here is being tested to see if it falls between, this is called the lower bound, and this is called the upper bound. And you'll see a message saying chi-square test at 5% level passed if it does fall between those 2 values. If the total error is lower than the upper bounds, or the lower bounds, that's the scenario we're looking at right now. That means you'll see a statement saying that the chi-square test has failed on the lower bounds, and this is what I call the happy problem, because it just means that your results are better than expected. So it's not not something to even worry about until you get near the end of the project. If you're looking at a scenario where the total error is higher than the upper bound, if it's, let's say, 5 or so, that generally means you've just got an outlier somewhere. You need to go through your data and look for some files or some observations that don't fit too well. Or the fourth scenario, which we're also going to see today, is that if the total error is a lot bigger than 5, like usually it's 10,000 or something, that generally means you've got a blunder in your network. So you've got a completely wrong height of instrument, or you've misnamed a station somewhere. A variety of other things can cause that. You might have picked the wrong state plane system or something like that. So that's what we're meaning right now. And so notice how right now it says chi-square has exceeded the lower bounds, and we're looking at an error factor of 0.65, lower than 1. That I'm not too worried about. So let's look at some of the other things on here. So here we're looking at just those RTK vectors, and notice how you've got these arrows, and so each of those arrowheads, those tell you how many redundant observations there are on this station, for example. So this station was shot 4 times using GPS right now. Something we're also seeing is over here we've got a warning. So in the error panel, either warnings or errors will show up, and they'll always give you clues. And you'll notice that there's a red highlight. And when you click on that red highlight, what it'll do is it'll jump you right to where in your input data that error came from. And in this case, it's just a warning. So that warning is there because STARNET has noted that scale factors were computed in Captivate while you're doing work, and it's just letting you know, don't worry about the scale factor. Because you've assigned the Virginia State Plane System, I'm calculating my own scale factors, so I'm not going to pay attention to those ones. And that's one of the big advantages of STARNET. It always takes care of scale factor, and you don't really need to think about it. Now, what I'm also going to do here is there's a few places where the scale factor was calculated in the field. So I'm just going to do a copy and a Control H. And I'm going to let's do a little search and replace. Everywhere you see scale, replace it with a hash mark scale. And we'll hit replace all. And that just means now I won't see that warning anymore. Let me just prove that. Run the adjustment again. Now we're nice and clean, and it's showing me the listing. Now, let's add some more data to this. I'm going to slide down here to where that data off was, and I'll just remove the data off. And now we're going to be including all of the total station observations. Okay. All right, so now we can see we've added a fair bit. All of these blue lines, those are total station observations, and you can see there's lots of redundancy, lots of arrowheads showing that these lines were measured more than once. And up here now you can see we've got a variety of different measurement types, and things are also tying together very nicely. We've got a total error factor of 0.7, still exceeding the lower bounds. I'm not going to worry about that too much because what comes up next is this next data set here, and I'll just check that one on. And in this data set, this is the one where a little bit of control observations were done, but then they went off and they sprayed in a bunch of detail shots up here, and it was actually a different day. And pay attention to the fact that currently we've got stations 1, 2, 3, and 4. And that might give you a hint as to what we're going to see next. So now let me run the adjustment again with that third piece of data. There's that scale factor warning again. So I'll comment that out just to make that less noticeable. And we're going to focus on the fact that here, this is the first time that we've got an error message. And so in this case, error messages again are always highlighted red. And this is a case where it's essentially like a syntax error, because what you'll see here is it's quoted the data line, that's line 40 right here, where there is an error. And with the story that this tells is that somebody had set up on station 2, back-sighted station 1, foresighted station 2. And STARNET says, hey, you don't do that, especially not when you've got an angle of 120 degrees here. And in the error statement, you see there's that row of asterisks. That essentially tells you where it is that STARNET said, hey, I read something that doesn't make sense. I need your attention to this. So it looks like somebody probably just named the wrong station. Apparently this was a training project, so somebody just kind of got things a little bit mixed up. And I'm also noticing up here, somebody has done a distance only shot between stations 2 and 1, where the distance is 367 feet. And down here, we've got a distance of 49 feet. So I think what I'll do here is I'm going to comment out this line because it doesn't make sense right now, but we're probably going to be able to make sense of it later on. And by the way, I've also commented out this distance only shot because notice how it's the same distance as before. So let's run it again, and we should have addressed that one because we've just taken that out of the project for the moment. Okay, now we've got to run. No more syntax errors, but let's have a good look at the processing summary. So what's happened right now is STARNET tried 10 iterations to come to a solution. It could not. And it calculated the statistics, and notice how we're looking at an error factor here of 12,000. So that kind of means your error level is 12,000 times higher than you would normally expect. And you'll see up here as well, the error factor regarding angles is the highest number. So that generally tells us there's something wrong in some angles, and that just kind of cascades through the whole network, and it probably affects all the observations. And you might have noticed also in the plot that the network actually kind of became a little bit distorted by those by this poorly mixing data set. So I'll talk about both the traditional way of addressing that issue and the a newer way. So, and that's the listing here, which I'll just bring up the appropriate PowerPoint slide. The STARNET listing uses the listing index tree. That makes it easy for you to jump through the listing and learn more information about your network. And so that's the listing here. I just switched to the listing tab, slide that down, and I'll pick on the listing index tree here. And what I want to have a look at is if I've got a problem with angles, what I want to do is go into my listing, into the adjusted observations and residuals section. And in this case, let's start looking at the adjusted angle observations. If I slide this a little bit wider, so we can see here is every single observation in the network. And they're kind of sorted so that the worst fitting observation is at the top of the list. So if you have a look at the STDRES column, that number is essentially a ratio. It's the ratio of what the residual was. So that means STARNET had to change that angle by 361 seconds in order to make it fit, versus the standard angle. The instrument settings that we gave STARNET told it to expect it to only change by that small amount, and this is just a fraction. So it's this number divided by this number, and that gives us a number that tells us that the error is about 63,000 times bigger than you would expect in this type of a network. And so it's typical to, and now you can see the file line over here, so if I double click on that, it's typical for these, or for a traditional STARNET user to go in and, okay, well, let's see if I just comment that one out. Does that solve the problem? And it's kind of a reiterative process that you go through until your data comes through nice and clean. That's one way of doing it. Or there's a tool here that's called Auto Adjust. I'll just bring that up on the slide. And Auto Adjust kind of automates that feature. So we just go up here. It's a special run type mode right next to the regular adjust network. When we run it, what it's going to do is it's just going to do a run. It's going to look at the worst observation. It'll unweight it, and then it runs again. and it'll keep on doing that until the chi-square test passes. So see how it's had to do it about 6 times, and now I've got a much better result. I've got I'm back to exceeding lower bounds. And the reason, or the feature that I want to have a look at, and also something that I should caution you on, is the auto adjust feature. Think of it more as a diagnostic mode, and what it does is it makes it much easier for identifying those outlying observations and fix the problem. So back to the listing index tree, and we'll see here we've got a special section in the listing now, auto adjustment observations removed. And see how what it's done is it's identified that the first time through, that observation on line 42 that we looked at before was unweighted, and then it tried to run again. And then it found, so first it took out the angle, and it still didn't pass, and then it also unweighted the distance, it still didn't pass. Then it went on and it found that line 41, that's this one here, was a problem, and it's gone through and 41, 41, back to 42, and then finally line 33, it unweighted that one, and then finally things passed. So an easy way of solving this problem is, yeah, let's just do what we used to do in the old days. Comment out line 42, I'll comment out line 41, and I'll go up and I'll comment out line 33. That one didn't fit too well either. Now I can run my adjustment, and our chi-square passes. So that's great. And then now something else to note though is I have a strong feeling, I'm sure almost everyone has noticed that these ones are all dealing with stations 1, 2, 3, and 4. And remember, stations 1, 2, 3, and 4 were part of the main control network. And it might just have been that the second crew didn't know that stations 1, 2, 3, and 4 were being used, and they just reused them. So what's a way of taking or returning those observations in, but not using them? One of my favorite little tricks here is just rename the station. So I'll add an A to the station name. I'll add an A to that station name. And I think I'll leave that one until later on. So let's run it again, just to see where stations 3A and 4A fall. So what I can do is I can click on the station name and it just centers it on the plot. I'll zoom in here. There you go. So there's where 4A and 3A were. So they were just misnamed station. And now let's have a look. Remember this one that I had left out a little while ago, because again, I was suspicious that somebody had misnamed a station. And notice how these two observations, the distance is exactly the same. So I have a feeling these are shots on the same station, and we just have to give it a different name to see where they fall. So how about I'll comment these two observations back in, and let's make it station Z. See if that'll run, and see if that'll produce a station Z. Yes, there it is. So that was clearly not station 1. And then finally, this one here, I think now that we're not touching on station 1 anymore, I think all we have to do is comment that back in. Let's see if that fits. It does. Okay. And now you'll notice as soon as I added that, you can see that the chi-square error level went up a little bit, and now we've got a passing chi-square test, and we're almost at the end of this process. Now, last thing that I want to go into is notice how we've kind of got color coding in the network plot that helps us to interpret our data. So we've got red for our GPS shots, we've got blue for our control shots or for our main network shots, and then in here, what STARNET has done is it's classified a series of detail shots as side shots. And notice how they have that green coloring. And that's because, remember when I set up the project, I turned on that side shot detection feature. And the reason this, now I can circle back to when you're using an AP20, this is a data set where when the control work was being done, the targets were all being properly leveled. All procedures were being followed so that the results you expect from a 1-second instrument are the results that you're going to get. But note that if you're using an AP20, I don't know if anyone's done any academic studies about this, but the majority of people I talk to say if you're using tilt correction, no, you don't expect a 1-second instrument to act like a 1-second instrument. You just, you're not too concerned about high precision. What you're concerned about is productivity and safety. And so for that reason, STARNET has this feature where anytime you take a shot and you haven't touched on that shot in any other way using the network, it'll classify it as a side shot. It shows it as green in the plot. And this is also more important. And I'll just get on to the last part of our presentation, which is understanding your output. And so this is where we want to pay close attention to whether or not a coordinate that you've calculated should be classified as a side shot, which would be a useful coordinate, but not one that you'd ever want to use in future surveys versus a control point. And if we look back in the listing index tree, there's this important section here called error propagation. And so what STARNET has done is for each of the points that are touched using the blue lines, it's calculated, in this case, a standard deviation. And down here, it's also calculated a semi-major axis or an error ellipse. And if you need to do alta positional tolerance testing, it's calculated a relative semi-major axis. But that's only for the stations that are considered network points. If you go further up here, it has separated out all of the stations that were observed just once, and it's only showing you the coordinates without any weighting. That's because STARNET calculated them after it calculated the main network, and we don't really have any statistics on it. And that's exactly the way you want it to be. Your tilt-corrected shots, you don't want people using those as control points unless it's a special circumstance. And also in the coordinate output, what STARNET has done is it's arranged things so that all of our control points are at the top of the list and all of our topo detail shots, they're at the bottom of the list. And so now that we're at the end, how are you going to report your results? This tab here is very simple to understand. That's a coordinate listing, and if I go into my project files here, notice how there's a file with the extension PTS. That's the coordinate listing. So that could be read into a CAD program as a space-separated ASCII file, and you're good to go. The listing file here, that's the LST. That's also a notepad document, and that can be included with your results. So that whenever you're reporting results, if you want the person receiving them to be able to have a really detailed look at all of your results, then that's in the listing here, and that you can submit along with everything else. In terms of output, I've talked about the main things. You've also got the option of exporting a DXF. If you want to be able to output a DXF file and just place it in the background, usually people put it on a frozen layer in the background of the CAD drawing so that people can see the error ellipses, but I won't show you that one, but I will do a KML export, just so that we can open it up in Google Earth and zoom in and see that everything makes sense against the background imagery. If we zoom in here, we can see there's the main control network, and over here we can see that an AP20 was used for curb and gutter shots. You notice how I've got the one shot here is still classified as blue, and remember that was station Z, where remember there were actually two observations on Z, the distance only as well as the angle and distance, and just because it was shot twice, it's classified as blue. If I really wanted it to be green as well, then I would have just commented out the distance only observation. Okay, now back to the PowerPoint, and let me get into my summary. So remember back to my escalator pitch story where I was talking about experienced STARNET users will always talk about, first thing they always talk about is STARNET makes it really easy to find mistakes. And this is also what's really cool about the new Leica TS20 total station, especially when paired with an AP20 tilt correcting or auto pole. The AI features of the TS20 make it a lot harder for you to have the types of errors that can be caused by misnamed stations or by the prism tracking following the wrong prism, or with outlying errors and things like that. So the TS20 does a really good job of helping to reduce the chances for errors like that, which I showed you at the end of the day STARNET can catch if the TS20 doesn't prevent those things. Everybody will also know that two of the most common errors in any kind of conventional field work are if somebody input the wrong target height or input the wrong instrument height. The TS20 plus AP20 are magic in that regard because it measures its own instrument height and it automatically measures the target height. If you change the target height, it updates and it gets recorded in the data file. So they do an awesome job of taking those very common errors out of your field work. But if you don't have one of those instruments, that auto adjust feature I showed you earlier, it's also very good at spotting target height and instrument height errors. The TS20 also helps to increase precision because it's a very high quality instrument. And when combined with a tilt correcting auto pole, it increases efficiency because when you're just going out and doing detail shots, it gives you a lot more flexibility if you've got tight visibility. It gives you a lot more safety if you're, say, running around on a road and you don't want to have your eye focused on a level bubble all the time. And then STARNET advantages. So advantages of using STARNET with the AP20. First of all, it simplifies combining data. You saw how easy it was for me to combine RTK and GPS. And remember, it takes care of all the scale factors and the T minus T corrections to angles and all those kinds of settings. It will always output as a grid file. When we look at that coordinates file, that there'll always be grid coordinates, but there's also a feature called ground output that allows you to output a ground scale file. STARNET is also very good at rapidly identifying common errors. Misnamed stations, outlying observations, you already saw. Incorrect target height, incorrect instrument height, auto adjust, also very good at those. And in the listing and in the coordinate output, it's very good for identifying tilt-corrected observations so that you don't accidentally identify those as control points, which could add imprecision to your future work. And bonus, STARNET increases your precision because now you're using least squares adjustment. And it also gives you weighted and very well documented deliverables. That is my summary, and on to the next page. I'm hoping that we've got a few questions from the audience. Thanks again for listening to me go on and on. I don't know if there's a chance, Dave, to do the mics open, or did any questions come in the chat line?
Yeah, well, we had, there was a couple questions leading up to this. I don't see a ton of questions in the chat, but I believe I can open up this Q&A, or somebody can hit the button to raise their hand and I can unmute them. But one of the questions that we got beforehand was, once a user has configured a typical STARNET project, how can they save that for the future so they don't need to reconfigure every project?
Yeah, I should have said that. Sorry about that. Yes, this is, there's an easy answer there. So yes, that person asked the right question. So all these settings that I flew through here, you don't want to have to do those every time you make a new project. So yes, let me differentiate. project, if you look in the options menu, you've got project options here. So those apply to just this project, or company options. These essentially are your defaults or your template settings. So once you've identified what your instrument is, populate this, save it, and these will become, the next time you create a new project, the company options will be applied.
Very nice. Let's see here. I'm gonna hit the Q&A button, but I still think you have to post your questions. Well, if no one has any further questions, you can also email us if there are questions after the fact. We have discussed that we'll create videos to answer the questions and attach them to a recording of this video, which will be posted on MTS's YouTube channel. I see there's a couple people typing, so if they get out, just
You're
good
welcome to
presentation.
Rick. You're welcome to Brent.
Yes, thank you, Rick. Thank you, Brent. So again, a recording of this will be posted to our YouTube channel. So if you missed any of the beginning portions of the webinar, you can find it there. We're also going to be running some Q1 specials on MicroSurvey STARNET and the new Leica TS20 robot and AP20 pole, which were featured in this data set. And everyone that attended or subscribed to the seminar will get separate emails with all that information. And we do have a question from Tim, which says, can you show how the instrument library works, copying instruments into the current project? Oh, yeah. Sorry about that. My phone jumped at me while I was reading that.
No, actually, I just saw it just came in. Yeah, Tim, I'll be happy to show that. I might as well just answer it right away. It's a little bit of a talk, but if there's anybody else that has any questions, go ahead and jump in. I'll do this one after everybody heads off to their day. And Tim, if you don't mind just hanging on. Nope, no more questions? Okay, I will talk about instrument library then. It's a good question. So instrument library is a tool that it sounds like Tim's already familiar with it. Remember, up until now, we talked about configuring our project so that we're just using it as if we're only using a single instrument. But in real life, you frequently are using more than one instrument model, and sometimes you've got a mix of different types of instruments. You might be mixing a 1-second instrument and a 5-second instrument, and you don't want them treated at using the same weighting. So there's a feature also in here that is called the instrument library, and that essentially allows you to set up. So if we go to company instruments, so this is a way of defining a variety of instruments that can be used in all of your projects, or here we've got project instruments, and this is a way of defining more than one instrument, and they'll be saved with your STARNET project. And it's good to do that if it's a project that you have multiple people using. Let me set up a couple of project instruments and just show how to make use of them. So I'm going to make a new company instrument right here, and let's say that one's going to be the TS20. And okay, so I won't be too fussy about the actual setting. Let's just leave it at the defaults here. 0 centering. I'll say okay here. And then what I want to do is create, oh, sorry, I made that a company instrument. I wanted to make that a project instrument. Project instrument. Okay, so this one, I'll call this one the TS20. Hope that doesn't cause a conflict. And I'll leave the settings as they are. They're not going to be correct. And let's make another company instrument. I could call this one TS20, let's call it vibration. So let's say this is a case where you use the same instrument, but the conditions were such that you were on a highway overpass where you've got a lot of vibration. And what I might want to do here is just allow for more error in the zenith because of that high vibration. And let's allow for 0.03 of a foot of variation in your vertical observations. So I can pick on OK there. And then if I want to implement those two, and sorry, I made this one a company instrument again. So if you want to implement them, then let's go back to, I'll say that with my control observations, let's say I use the TS20. So I just type .inst, and then notice how it actually allows you to select from the pull down. And I'll tell it for this data set, we use the TS20 and we want to apply. So what's going to happen is the settings that I put in the instrument library will override the settings that are in the project instrument settings. And then let's say that over here in the side shot section, where we did a bunch of detail shots, let's say it was poorly set up. So I'll use DINST. Oops, got to be a .inst, and then in this case, we'll use the TS20 vibration model. So this one is expecting your results to be less precise. And so what this will do is this will greatly affect how the error factors are calculated, and they will greatly affect the chi-square test. So when I run this again, we're probably going to find that we see a very different result. There we go. So notice how it's now exceeding the lower bound, and that's largely because I just left the settings in there with the default settings, which were for, I think, for a 5-second instrument. So now we measured everything with a 1-second instrument, but STARNET is now saying, hey, your results are too good for that. So it's giving you a chi-square exceeded the lower bounds message. There's the instrument library. Does that make sense, Tim? You've been using STARNET since MS-DOS. I am impressed.
All right. Does anyone else have any last minute questions for James? Huh?
Okay, well, Dave, thanks again for inviting me. I enjoyed this, as I always do. And sorry to everybody because I went overtime. Dave had commented, somebody said, James is probably going to go overtime, and he was exactly right. Thanks
No
everyone
worries.
for staying.
We appreciate it. A lot of good info. And just to say again, everyone will receive another email from us with a link to the recording of this video along with some other information. And if you do have any other questions or need anything else, please feel free to reach out to myself or James, and we'll be happy to help you out. So
Great.
have a wonderful weekend. And for you, those of you in the Northeast with me, hope you stay warm.
Yeah, and have fun with your snow shovel.
Yeah. All right, guys. Have a good one. Thanks a lot.
Bye-bye.
See ya.